Today I'd like to show you a demonstration model from Endevco. It's called the sliding bar model, and it's designed by Professor Stutz at the University of Missouri at Rolla. He was inspired by an old problem that you find in a bunch of vibrations textbooks, and thought, gee, I'd like to build one for real life. And then Endevco, an instrumentation company, built it for the university forum, a consortium kind of trying to support university teachers, and coordinated at that time by Dr. Patrick Walters at TCU in Fort Worth. So here is what it is. It's two counter-rotating drums or pulleys. They're counter-rotating because there's this linking rubber band belt that keeps them going that way. And it's got some little notches here to help you turn them. And you can set the bar on here, and you discover that it oscillates. I turned a little so it wouldn't ring as much. And so the question is, how do we explain this oscillation, and how do we write an analysis for it, which is essentially the textbook problem that we're addressing here. Now, the thing that's puzzling here is that there's a mass, but there's no spring. These things are rotating sufficiently steadily that for this particular case the rubber band doesn't actually flex. It just keeps them rotating. A lot of inertia here, they're rotating pretty steadily. And the explanation, of course, is that the heavier side has more friction. So if this thing is over here, then most of its weight is on this side, and if these are rotating towards each other, it'll push it towards the center. If it's mostly over here, it'll be mostly on that side and push it towards the center. And we start rotating them, and we get a steady oscillation. This is basically the stable problem. If we reversed rotation, had them rotate apart, of course, whichever side it was on, it would tend to go even further in that direction and would fall off. It would be a divergent solution. So let's look at how we would analyze this and then rotating and see what we can make work. The basic model of friction that we use for real simple first order analysis is called Coulomb friction. It says that the force, tangential force generated by the friction, is constant and independent of velocity, except if the velocity reverses, then the force is also in the opposite direction. And that's the simplest dry friction model that there is. So if we can build an analysis on that, and the way we do that is we'd first go back to our statics course and figure out how much more weight is over here than over here as a function of the deflection of the center. And what we find out is that the weight difference is proportional to the displacement. Then when we say, hey, the friction force is proportional to the weight, then the net difference in friction forces is also proportional to displacement, and we get a centering force, and we can spin this, and it gets a steady oscillation. I would say the period seems to be about 1 second, so it's about a 1 hertz oscillation, and it just keeps going. And now once we have these equations down, we find that our dynamic equation looks like a vibration equation. Here's the mass, and then the spring force is provided by friction instead of a spring. And so there's a restoring force, and we get a sinusoidal oscillation, what was called a harmonic oscillation. And if we do the analysis, we find that the frequency is proportional to the friction factor. Now we have to be a little tricky here because the contact force here is actually 1.4 times the weight because of this V notch, but we can calculate all that out and find out that for this particular combination there's a 20% coefficient of friction. and we could try different materials to get different friction coefficients. We use this as a testing machine for friction. We could also degrease this to take all my skin oil off it and maybe get a little more friction, or we could oil it up and get a little less friction. So it's kind of a little thing we can play with. Now all this is the simple theory. What happens when we observe this? Well, when we observe this, we find that besides seeing an oscillation, we also see that the oscillation grows a little bit and is self-sustaining. So how do we explain that there's energy transferred by this system to the oscillating bar? So it raises a question, and to explain that, we have to find a way of explaining the energy transfer from my cranking into the oscillation. And that can actually be taken care of by modifying our Coulomb friction model a little bit. And what happens is that we say that as the velocity increases, the friction factor decreases a little bit. Now I've observed that when I'm on the highway driving my car, to get a certain rate of deceleration at high speed, I have to push the brake pedal a little harder than I do at low speed. So that's not entirely unexpected, and we can include that in an analysis. The kind of analysis we need involves now some trickier nonlinear terms, and you can use the analysis by Krylov and Bogolyubov, for example. If you have a vibrations book like my vibrations primer here, that would be chapter 38. Shows a simple method of approximate analysis for that kind of effect. The trouble is that that's not the only thing we observe. As we observe this, we find that yes, the amplitude grows, but it approaches a limit cycle. It doesn't keep increasing until it shoots off. So there must be even more going on, and we can push the analysis a little further and find that we must have an even higher order effect on the friction factor that causes it to grow in a certain regime and then reach a limiting amplitude and not grow anymore. And even if we kick it fairly hard, it comes very gradually, because this is almost a straight line, to some kind of an equilibrium amplitude. So if we keep our eyes open, we can observe all kinds of interesting things, including the fact that when we first start out, it looks a little weirder, because it seems like this kind of rides back and forth, kind of occasionally sticking to the pulleys. And that's a much more complicated behavior, but it's something that, again, we know that sliding dry surfaces have something called static friction, or stiction, in addition to the dynamic friction, which is roughly straight or maybe a little bit sloped and curved here. And depending on the particular combination, that static friction can be quite a bit higher than dynamic friction. And so what can happen is that when this starts out, one side happens to be a little heavier, so the other side breaks loose, and it'll kind of ride along with that side for a while. So that's a trickier phenomenon. We can't do it analytically very well, but there are, in my primer, for example, chapter 36 shows graphical methods in the phase plane where you can plot the velocity and displacement history just by purely graphical means with a compass and a ruler, and not have to do any higher math at all. And that's another interesting challenge for somebody that wants to explain systems like this. Now, this is kind of an idealized problem, but this kind of phenomenon occurs in a lot of autonomous oscillations involving friction. For example, belt sanders or chattering machine tools. There can be a lot of phenomena, vibration phenomena, that arise unexpectedly, and that can be a big problem, and this is an easy introduction to this. Now we can play other games with this. We can keep this in contact and do oscillations with a rubber band here, or rotate these and observe the observe the combined oscillation of two rotating masses, and so there are other problems in there, but the ones that involve this rubber band I don't want to address today. I think this is really interesting from the viewpoint of just seeing how autonomous oscillations can come to be. I hope you enjoyed that and that you get something out of it.